typically, you would, yeah, we sort of go sort of 2, 5 to 10 minutes for questions. Are you going to connect it on? Can you connect it to the? Yeah. Okay, let's start. Welcome everybody. It is my great pleasure to introduce today's speaker. I'm Sudakow from the Open University in the UK at the moment. Ivan hails from Russia, did his PhD in mathematics in St. Petersburg, and then moved to the University of Utah, where he worked on sea ice with Ken Golden as a postdoc for 3 years or so, and then spent 7 years on the faculty at the University of Dayton. And most recently relocated to the Open University in England. Now, he's visiting the University of Chicago for 1 month as a visiting research scholar, and has an extremely packed schedule, I just learned. He is not only in this month doing the research visit in the University of Chicago, he's here. He's also going to Ohio State and is a Kavli Fellow, so he's going to Santa Barbara in this time as well. So yeah. We're glad we could nab you for this talk. He's done a lot of interesting work on several aspects of the mathematics and physics of climate. And we're very excited to hear today about the mathematics of climate's tipping point. So without further ado.
Yeah, thank you so much. Thank you for the invitation. Yeah, I've been trained like as applied mathematician and physicist, but since even my PhD work, dissertation, I'm working on this climate application, and I will talk about different things today, some of them related to climate and atmosphere, but ocean, some of them just very general things, and it's this work can be named like mathematics of climate tipping points. And first I want to tell about the tipping points and the tipping elements and the climate system. This is the theory that came from Tim Lenton, who is an Exeter in England, and now it's like the first paper, it was like 15 years ago, but now it's developing very well, and even it was a big conference on climate tipping point last month. And we also published a new paper where we revisiting this concept, because this concept appears in the IPCC reports. In the recent reports, it's already some kind of a few pages on that, but it will be more and more. So tipping points, it's a very general term what cannot be defined rigorously, but in our terms of view in mathematics, it's close to bifurcation in dynamical system, but the general definition, it says when climate system goes from one state to another state, and this change is rapid, irreversible, and they have significant impact when its so-called climate tipping point happens. But now a lot of questions like irreversibility. Now some of we think some tipping points reversible, but Anyway, and here you can see potential tipping elements. So where these changes can happen and switch the state of the whole global climate system. And this is a new work just published in September where we evaluated the risk of these tipping points. Some of them very dangerous because may happen recently, or some of them we need to increase the global average temperature like by 4 degrees. And I'm particularly concentrating on the Arctic region and these tipping points related to permafrost and sea ice. We think it's not really dangerous, but anyway, they see the Arctic is in rapid transition, and it's not something new. The sign of transition really visible, but at the same time, we need to develop the understanding of processes in the Arctic system and make a call for physicists and mathematicians to study climate system, not only Arctic climate system, general climate system. And it was many efforts happened over the last 10-15 years in this country, in UK and Europe, when physicists, mathematicians, climate scientists, they conducted joint research and got a lot of interesting results. But it's not only modeling, it's the main thing is the understanding of these processes, the mechanism of this process in the climate system. So in terms of modeling, because mathematicians, we just making models, what we can say, the global climate models and the Earth system models, they based on the Navier-Stokes equation, on the equation of mathematical physics, and if we can parameterize, if we can get real data, we can solve it numerically even, and it's a good progress. But the models, they still have this constraint, but not really good, because some processes we cannot understand and cannot predict. And some interesting challenges here, it's the resolution, for sure, 50 kilometers, the resolution is not good enough because many microprocesses influence on the climate system, like microbes, for example, in permafrost, or algae in the Arctic Ocean, and the model cannot get it. Also, the links of different scales, it's an important factor. We know we have like couplet models and everything like that, but it doesn't work really well still. And many processes in the climate system nonlinear, and we have a critical behavior and simple equations what actually the fun underlying these climate models, this equation cannot count this nonlinearity and criticality. And there is another way how we can model a climate system to understand the tipping points. We can employ this dynamical system theory, bifurcation. We can consider whole planet like a dynamical system, and when if we have some state variables and we can change the potential of the system, so it goes from one unstable state to another, from one stable to another stable, through unstable and metastable states, and when critical points are happening. Or in statistical physics, we have a phase transition theory, and we can employ the same ideas. The state of the climate system goes from one state to another due to changing the order. And like switching order disorder in this system because the energy is changing. And all this concept actually now it's popular in climate science and physics. But also another way just recently developing, and we just published a paper on that. It's about climate simulators that combining low dimensional models and real observational data and based on machine learning algorithm. We're learning the real data, how the processes, how it goes actually, and feeding some stochastic models, low dimensional models, and when such model can emulate different processes, not compared to these global climate models, we are not actually incorporating very detailed physics where it's just one or two physical parameters, and because such models stochastic, they have statistical nature, and machine learning helps to study real data, and a combination of all these efforts can give the emulator what cannot predict, make some prediction like global models, but actually can give million scenarios what we need to learn and understand a possible way for the climate system. And today I will concentrate on two elements of the Arctic climate system: Arctic sea ice and permafrost. And for the Arctic sea ice, the main problem to model, to incorporate sea ice albedo feedback, what could be a major driver of the energy balance in the climate system. And since it's some data, not maybe even really new, but we can see the ice coverage is summer sea ice extent is decreasing every year, and it's actually contributed to the sea ice albedo feedback when ice is melting, lowering albedo, the reflectivity of sea ice, changing the energy balance, the ocean absorbing heat, and ice is heating up and ice is melting again. And then it can be a good contributor to the global energy balance, even more than CO2 emission. And the ice albedo feedback should be, we need more and better understanding of this feedback. Same thing for permafrost carbon climate feedback. Permafrost is a frozen ground officially for 3 years. If it's frozen for 3 years, it can be counted like permafrost. And permafrost storages huge amount of carbon, frozen carbon. But since it's melting, the carbon is the bacteria actually living in permafrost. They're eating this carbon and releasing methane, what is again dangerous greenhouse gas. And since the permafrost carbon pool is very huge, 1 billion tons, it's now it's a problem again how to understand permafrost carbon feedback when methane releasing, the atmosphere warming up, and permafrost is falling again, and more methane releasing, and so on. And again, the mechanism not really clear. Just we know what's going on, but the role of different processes is not really clear. But again, methane is a good contributor to the energy balance, radiative forcing. So we need to study and understand this permafrost carbon climate feedback. So in this talk, I briefly tell you how we can employ bifurcation and stochastic theory to study tipping points in the climate system. But still, it's a very difficult problem to study climate system, because I said the link for sea ice, for example, and permafrost, they need to connect in all scales. from microbes, from algae or microbes and permafrost algae in sea ice to tundra lakes, melt ponds, and the global energy budget of the climate system. So everything is really important, and everything is nonlinear and stochastic. And when we need to even basically understand, develop a theory how to understand this process. And all this work done in collaboration with many collaborators. Even I took part in the field work on the Arctic sea ice. And let's see. So this nice picture, so-called melt ponds on the Arctic sea ice by the end of melting season. I just want to show a video. So what is melt pond? Actually, every summer the snow cover and on ice pack is melting, and some ponds are forming on the surface. And these ponds are not really deep ones. The depth is less than 1 meter. But since we have temperature rising, and since the 80s, we see more and more ponds on the surface of the Arctic sea ice. And when actually we're decreasing the albedo because it's water, it's reflecting solar radiation, and then contributing to melting. And at the beginning of season, it's usually June, the melt pond coverage is extending and albedo dropping. And this we saw such transition, critical transition in statistical physics before. So this one, it's really remaining some processes of phase transition in statistical physics, but actually it's like a natural process, and it needs to be understood why this growth of melt pond coverage, the albedo actually quickly and drastically changes. And melt ponds, it's a main driver of the polar climate, and it's a key challenge for global climate models that actually can model sea ice, but sea ice usually the model is the equation, the thermal conductivity equation, and it cannot count like forming of this pattern on sea ice surface. That's the main problem. They don't know how to use ordinary equation to model these patterns. And when we need to find another methods to model even numerically these melt ponds. And these patterns look like a nice kind of complex system, and it's really complex system because Ken Golden and others, we analyzed about 5,000 images of melt ponds in the summer season, and we found we critically changes from simple circular pond to a complex structure, and the geometry of these patterns is changing. And from the images, we can measure perimeter area easily, the geometry, if you have satellite or helicopter images. But in mathematics, we can connect both perimeter and area. If it's a simple shape, whereas the connection is pretty simple between perimeter and area. If it's a complicated shape, we need to find so-called fractal dimension, what characterizing complexity of geometry of the system. Fractals are self-similar structures, but melt ponds not a fractals. They use just this parameter fractal dimension to describe the complexity of the geometry. And what we can see, fractal dimension critically changes at 100 meters squared. As I said, from really simple ponds, quickly we becoming very complex structures, and the complexity is changing. and the fractal dimension, so it's changing, and it's a good parameter to measure complexity of different natural patterns, from clouds to tundra lakes, for example. But if we want to find in some interdisciplinary examples, we can look at thin films of cobalt or magnetic domains of cobalt, and they see it's a microns, but they see similar patterns, and also these materials, they have optical features like meltpoints. Meltpoints, they have optical features that they change in albedo, and these materials, magnetic materials or films, they change in optical features of the system. But the scale is really different. And to model meltpoints, just pattern formation, they actually recall a model from statistical physics, what called the originally called the Ising or Ising model. Also, maybe if you just looking from statistical point of view, it's called Markov random field model. But what's the main idea? If in 2 dimension we have a variable on the lattice, and this variable can get only 2 positions, up or down. It's so-called like spins, spin up or spin down. And doesn't matter what you're modeling. You can model tropical convection, meltpoints, magnetic materials. It's just a system. And the spin can be numerically can be represented like positive one or negative one, but it's flipping the some probability. So the system, the spins actually the nodes of this lattice, but we have some probability when the spin randomly flipping up or down. And this probability is actually the function of energy of the system. And what is usually energy of this system? This is the interaction between neighboring spins, because we have influence and through like energy transfer, for example, and we can flip. And also some external field. If you have a magnet and you can get some external magnetic field, you can change with spin too. So as I said, it can be applied to different things like magnets, because we have these magnetic moments in materials, magnetic moments, and we switching position with some probability, what depends on the energy. And when the structure of this material is changing from ordered structure, when we have so-called ferromagnet, when this magnet can attract other metal things, right? To paramagnet, then the structure is disordered, and the spins will have different position. And anti-ferromagnet when it's opposite material. And the main driver way is the temperature. Increasing temperature, so-called the Curie temperature, you making disorder in this system, from order to disorder. And the order is really important because it has this magnetic feature, and disorder, it's a paramagnet, it has no features. And also this model is been applied to model tropical convection. Some convective in when the convection is forbidden some places, and some places where convection is allowed. So you also have like 2 spins, system with 2 spins, and easily can be modeled using Monte Carlo simulation. So it's another positive thing for that model. Concerning now meltpoints, we can also represent them like a system with spin up, it will be water, spin down, it will be ice. And in our case, points also interacting neighboring points with transferring energy from between neighbors. And we have this external field not magnetic field, of course, in our case. And this field is a pre-melt ice topography, because at the beginning of the melting season we have snow cover, and the ice pack is not smooth. Ice pack has some holes, some hills, and it might be like this one. If you need to learn real structure of topography, you need to do just to make some field, to go and get data from field work, but generally it's really random. I mean, the topography of sea ice. And when the driver of the system, it will be melt pond fraction, the fraction of spins looking up. And actually, the positive thing of this model, that we need only a single physical parameter, the topography, the pre-melt topography, this parameter h, to run this system, and nothing else. So one parameter, and you can run and model these patterns, melt pond patterns, what I want to show here. The Monte Carlo simulation. So they see also tendency, like ponds from isolated ponds, they actually transferring to some clusters. It's an important feature in terms of physics of this system. And in real life, we also see from a little isolated ponds to clusters. We can explain it through the concept of metastability in physics. We have unstable states of the system when a ball, for example, on the top of the hill, and after it's unstable, it goes down, right, and it's stable. But for such system, it's something metastable state, something in between. And these ponds, it's a metastable state between the smooth ice pack and the ocean water. And the important thing, how to validate this model. They actually made this Monte Carlo simulation and measure it same geometry, fractal dimension versus the area. And here is the modeled one, and here is the real from real data, and we see this transition close to 100 meters squared from our simulation. So this model works good because it's validated and it's really okay. So we can implement this model to global climate models next. But also it's a good new step for physics. From this model we got a new class of statistical physics model with feedback. Because for melt ponds, this feedback, if pond coverage is increasing, then actually the albedo is dropping very fast. But it's like an interactive process, and more coverage and more interaction between ponds happening, and they try to be to actually congregate in clusters. It's a new theory, and also it has social science application to study, to describe people's beliefs, how from isolated groups, these beliefs, they becoming like congregation of churches. We work on that project now, but the mathematics is the same one, like for melt ponds. And finally, where we can get this topography, we can get it from satellite or helicopter optical images, and we developed the algorithm to detect, to classify melt pond images and detect different classes of like melt ponds, snow, and so on. And also, it's like real data, but because we cannot go to the field and measure this topography because it's a random. Today is one kind of distribution tomorrow in our life. But we can run so-called GAN, generative adversary networks, is a machine learning algorithm, what can allow not only analyze real pictures and get data, like here, white color is corresponding to the ponds, melt ponds, but also it can produce so-called fake patterns. So the network is learning from noise, how to produce patterns similar to what we have in real, from real data. And why we need it? Because we can have millions ways to model this topography, to get the parameter from our model and million configuration of meltpoints. But computationally is easy. It doesn't require any computational resources, only PC, and it's okay. So this is about the meltpoints. Another critical element, tipping element in the climate system is tundra lakes. And here the satellite image of tundra lakes. And again, some people looking, and one journalist told me, what is it? It's like molecules. But I said, no, it's tundra lakes. And again, it's some kind of cross-pollination. If people like with meltpoints, they think it's really close to these thin films or magnetic domains. Here we can say, oh yeah, it's really something like you looking at microscope and see this stuff of these things called tundra lakes. What about the tundra lakes now? The tundra lakes is a great resource of methane. As I said, the permafrost storages billion tons of methane. And permafrost is pretty stable, but it has an active layer, what actually melting every year, and it's not refreezing. If you have melt ponds, every year we're refreezing, and next year it's a new cycle, new melt ponds coming. Here, no. And for permafrost, we have a different thing. This active layer is pretty stable during the winter, because here in the winter you have a snow cover, and snow cover it actually prevent the heat transfer, and it's stable. And every year, because the temperature in Siberia, for example, it's increasing every year, it's getting wider and deeper. And what's going on? These lakes, they actually expanding every year, and they contain a lot of methane, because active layer is a good environment for microbes. Even in winter time, they live there, and it's very nice for them. And these bubbles, like in even winter season, you can observe like a tundra lake in Alaska is bubbling. Katie Walter from Fairbanks, she's doing great job on that, and you can see on the internet many nice videos how tundra lakes are bubbling in the winter. It's methane. And the idea is to study the geometry, to understand the complexity and connect this complexity to methane emission models. To study the geometry, we need the same thing. We need data, for example, satellite data from Landsat, and we apply some machine learning algorithm to better detect these meltpoints and study their geometry. Or this series, not really long one, time series of data. We can even use old maps to detect the initial, like this map from 1979, to detect the initial shapes of the lakes. Maybe it's not really close, like not the same one like from satellite images, but it tells us something about the geometry, about size and how it's expanding or even shrinking. Because in some areas, the lakes not only expanding, they also shrinking because of this, processes, hydrological processes. Oops. It's like, okay, yeah, sorry. The hydrology, the water exchange between neighboring lakes. One lake takes all the water from another one, and this lake becoming like a peatland, for example. So the shape also is very important, but physically you cannot go and measure these lakes because the area is kilometers, and you definitely need some algorithms to measure the geology. But what we found, actually the fractal dimension, like the parameter of complexity, is very stable for the historical map, for historical lakes and current lakes. It's pretty stable, but still complex. 1.6, 1.7, it says about the great complexity. And also the size distribution, it's parallel distribution. It's saying about the complexity of the system, physical features like percolation and so on. But it's important. So how to model these lakes? Again, there's some simple way to get the thermal conductivity equation for soil, and that's it. But in reality, permafrost can be represented through so-called the Stefan problem, a two layers problem. So in the Stefan problem, we have upper layer when something is melting, material, ice, or kind of material. So the melting part, like ice, this stable part, solid part, and in between we have a melting front. And this is the good model. This is thermal conductivity equation for how temperature changing in the upper level, low level, and for this front, moving front, melting front. Very good model to describe permafrost, but the problem is numerically it's really hard to realize. And instead of that, they actually employ some ideas from statistical physics from superconductivity, so-called Ginzburg-Landau formalism. It's coming, Landau and Ginzburg, we got Nobel Prize for this description of this formalism, but the idea is a simple one. We have again like two spin system, falling soil in frozen ground and melting front. And to describe the how the lake is changing, these boundaries of the lake, they need to learn something about the melting front. Oops. Okay. And yeah, so and this equation will be helpful to describe this melting front and how the active layers melt. Again, some cross-pollination of like physics and permafrost. And finally, what we can do, if we think like on the surface of permafrost, we have tundra lakes, and we have a methane emission from these lakes, we can switch the dynamics of the atmosphere. Here there is a intermediate model for the atmosphere called the Goody model. What is a relay binary convection model? What is main thing for such model? At some point, when atmosphere is really stable, we can see so-called binary cells in these convective flows. It's sign of stability. But if we have a source like lakes on the surface, and we have the methane emission from them, like gas emission, so the atmosphere is maybe really chaotic, and we can get some bifurcation in the dynamics of the system. So here is the classical Goody model, what is relay binary convection. fluid velocity, temperature, and we introduce the gas concentration, the gas decomposition, because finally methane is decomposing. And actually this model is feeding the concentration will define the absorption of radiation. So the main parameter will connect all this part of this model. And these lakes we can describe for this function. What is like a function describing chemical reaction, the Arrhenius law actually. And this one is a function describing geometry of these lakes. So when they study dynamics of this model, they got many interesting things for mathematics and some new theorems. But for in terms of climate system, we got these nice results saying, but from this model we can compute so-called the methane emission level. We cannot say exactly how many tons of methane will be necessary to stitch the dynamics of the atmosphere to get a chaotic dynamics. But the methane emission level can be computed. And here it's parameter what is actually defining the state of the atmosphere versus the surface temperature. And it's a by stability here. It looks like we at this point at 300 Kelvin now, but this next, it's really unstable point, but next stable point will be when the temperature will increase and the level of methane should be increased in 1,000 or 10,000 times compared to the current level, when the atmospheric dynamics will be chaotic. What is the interesting thing? How we can, what is it? We can say the planet will be like covered by greenhouse gas fall, actually. So every day some kind of interesting kind of possible scenario for our planet. And finally, the main driver of these climate tipping points actually it's biosphere. As I said, methane emission, the microbes here eating frozen carbon, and on permafrost it's releasing methane and even CO2. Algae beneath sea ice actually changing the structure of sea ice and albedo of sea ice. And what we are working now, the NSF project, we have to understand the critical algae bloom beneath sea ice, because it's not the usual things. Algae are very neutral, usually in the Arctic Ocean, but we're blooming and changing the albedo. And finally, how it goes, everything goes to mass extinction through kind of mechanism. So how, because they have tons and tons carbon, frozen carbon, billion tons. When it will be this final point when it will be, this loop will be stopped, when these bacteria, population of these bacteria will, I don't know, will extinct, for example. And this carbon climate feedback will be finished, ended. No, it's a good question. And it's another direction of our research, and what we are doing here, for example, to understand how the biosphere dynamics influence on the climate, we connect coupling so-called population dynamics equation. If you have one sort of biomal population on the surface of your planet, and this species consuming for resource, and resource is a function of the temperature of this planet, and the energy balance go through this model, the energy balance model, Sudakow model, for example. We can couple all these three things through the albedo, because the biosphere changing albedo, so-called the daisy wort model, or the hypothesis actually. And in terms of math, it's also interesting kind of equation what we can solve, new kind of models. But in terms of global climate system, we can see with biosphere and change in the state of the climate system, and especially low biodiversity, it may be a trigger of a climate tipping point. High biodiversity makes this feedback and the state of the climate system very, very stable until some kind of mass extinction events. They actually publish a big review paper on modeling mass extinction now, and it's they found the killing mechanism really important to study to understand this extinction, because at some time the biosphere is very diverse, climate is stable, and you know, like this dinosaur time, but at some point something happening and the tipping point, and we have unstable system. So yeah, the main conclusion here, but our nonlinear and stochastic models very helpful to understand climate complexity, and maybe used in the climate models to predict the fate of the climate system and to understand the processes, the fundamental processes of the climate system. Thank you.
Well, thank you very much. Any questions from the audience? I bet there's lots of questions. Vijay?
I was wondering, so like regarding the melt ponds and the model that you showed, so if I was understanding it correctly, like, so there is the albedo feedback as a mechanism of why melt ponds are able to organize in that way, and I assume like because there is also like an initial topography that could also like be leading to that type of behavior. Is that correct? If yes, how do we understand like it is coming from albedo and not topography?
The ponds changing albedo of the sea ice system, right? And melt ponds coverage, what you can get from this model, just studying these images, modeled images, I think, not like, yeah, this one, coverage, just counting the coverage, right? You can say how albedo can be changed. So, and such ways, you have many ways for the coverage of these ponds, the distribution of these ponds, and then you can learn something about the albedo. So albedo you can study from the coverage, melt pond coverage. And here you're modeling melt pond coverage, these patterns.
Yeah, and so like the initial topography that we have, that can also play a role in how this coverage would change, right? Like in
Yes.
terms of understanding where that coverage, like once you have enough water, it organizes in this way.
Yes, exactly. The initial topography influence on the coverage and the future development evolution of these patterns. And every year we have different picture of them compared to tundra lakes. Tundra lakes pretty stable, and year by year you see even similar picture, but sometimes they're disappearing or growing. But here, yeah, every year, because since the topography is different, and every year you have a new coverage, new distribution of mountains. Yeah.
Building on that, so you're saying the only input into your model is the topography to start with. You don't take in like air temperature. And so is that
Yes.
saying that the organization of these melt ponds and the development of them is irrespective of any change in the air temperature? That these will develop in this way regardless of the air temperature, and you only need the surface topography to start with?
This is the idea, the research what melt ponds guys conducted, and it came from when? The topography, pre-melt ice topography is the main driver, nothing else. Yes, some variation of air temperature, yes, but it can be considered like a noise in this system. And it cannot influence on the stochasticity of formation. But they assuming when they modeling, they assuming in the summer period the temperature in the Arctic is pretty stable and not deviating a lot, close to 0, +1, -1. What we can see. Once, yes, if it will be like the case of the snowball elf or something like that, yeah, it will be different. And even I didn't show that slide. I want to show now. We use the energy model, the energy balance model. We incorporated the albedo of melt ponds connected through the coverage actually. And what they found exact temperature when we have transfer from ice to ponds, 2.2, from simple ponds to complex, 3.2, and when fully melting of the ocean, like all the ice packet will be at 3.9. I mean the surface temperature.
So back to your melt point Monte Carlo sampling. So in real world, does the melted pond refreeze in a year? Like
Yes, in every
I
summer,
mean, in the,
every September.
not over the year, but in the same year, do they refreeze? Once they melt, do they refreeze?
So we're melting and in the beginning of June and refreezing by the end of September.
So in your Monte Carlo sampling, this the spot that is melted has melted. Can they refreeze, or is it unphysical for them to refreeze?
No, they don't have this option to refreeze because the goal is to count the full coverage of the melt ponds, and then we don't need them to refreeze. We need them to form these clusters and calculate coverage and when albedo. Yeah, but now it's people from Reading, yes, we develop a good theory how this melt ponds refreezing is important too, especially for the processes in spring. So yeah, I don't think it's not really like I don't think it's nothing. I think the refreezing is also it might be an important contributor to this topography, pre-melt ice topography, but we need to study it.
I had one question about the tundra lakes and the danger of catastrophic methane release. So I don't know anything about this. Is the methane stored in that layer here? And what is the relation with the Stefan problem? How does it, as the
methane, the storage of methane in this frozen layer.
Okay.
It's an active layer where microbes here.
Yeah.
And we actually, when it's melting, the active layer is growing, right? We taking this carbon and producing methane. So, and the active layer is also forming the boundaries of these lakes. And we need to understand these connections.
Right. All right. Let's thank our speaker once more.